All right, everyone, welcome. Today, we're going to jump from the flat 2D world of Lewis structures right into the real 3D world of molecules. We're going to explore not just what they're made of, but the actual architectural rules that give them their shapes, and ultimately their jobs.
So, let's start with a question. You ever wonder why water beads up on a leaf, but oil just spreads out? Or why some things are gases and others are liquids? This stickiness, you could call it, all comes down to how molecules interact with each other, and those interactions are decided by one key thing.
And that one thing is shape. A molecule's 3D geometry is basically its personality. It decides if it's polar or nonpolar, how it talks to its neighbors, even what it does in your body. You know, a straight molecule like carbon dioxide acts totally different from a bent one like sulfur dioxide, even though they look kind of similar on paper. Shape is everything. Okay, so here's our game plan. We'll start with why shape is so important. Then we'll get our hands dirty with our first predictive tool, something called VSEPR. From there, we'll connect shape directly to that stickiness or polarity. And finally, we're going to peel back the onion a little further with two even more powerful ideas, hybridization and the king of them all, molecular orbital theory.
So, how in the world do we predict these shapes? Well, our first, and honestly most intuitive tool is the valence shell electron pair repulsion model. We just call it VSEPR for short, and it's based on a really simple idea. The whole idea is right there in the name, repulsion. Think about it. Electron pairs, whether they're in a bond or just hanging out as a lone pair, are all negatively charged. And what do like charges do? They push each other away. So the most stable, comfortable shape for a molecule is just the one that puts these electron groups as far away from each other as possible. It's just that simple.
And using it is a pretty straightforward three-step process. First, you've got to have the right Lewis structure. That's your foundation. No getting around that. Second, you count what we call electron domains around the middle atom. Now, a domain is just a fancy word for a region of electrons. A single bond, a double bond, a triple bond, or a lone pair. Each of those counts as just one domain. That's it. And then finally, that number of domains tells you the basic geometry.
And what's really cool is that these 5 basic shapes cover almost every molecule you're going to see. Got 2 domains? They're going to get as far apart as possible, which is a straight line, 180 degrees. Linear. 3 domains? They make a flat triangle, what we call trigonal planar, at 120 degrees. 4 gives you that classic 3D pyramid, the tetrahedron. And then you get up to 5 with a trigonal bipyramidal shape, and 6, which gives you a perfectly symmetrical octahedron.
Now here is a super important distinction we have to make. There are 2 kinds of geometry. The electron domain geometry is the shape of everything, all the electron groups, including the lone pairs. Think of it like the scaffolding. But the molecular geometry, the actual shape we see, that's determined only by where the atoms are. If there are no lone pairs, they're the same thing. But if some of those domains are lone pairs, the final shape of the molecule is going to be different.
And that's because lone pairs are basically the bullies of the molecular world. See, they aren't stuck between 2 atoms like a bonding pair is, so they spread out and take up a lot more space. They're just bigger, and they push harder. And this extra shoving actually squeezes the angles between the real bonds. So that perfect 109.5 degree angle in a tetrahedron gets squished down to about 107 degrees in ammonia, or even 104.5 degrees in water.
Okay, so we can predict a molecule's shape. Awesome. Now for the payoff. So what? Why do we care? Well, one of the biggest properties we can figure out from shape is polarity, which gets us right back to our first question about why some molecules are sticky.
Figuring out polarity is basically a 2-step check. First, you ask, are there any polar bonds in here? Meaning, do you have atoms with different electronegativities bonded together? If the answer is no, you're done. The molecule is nonpolar. If the answer is yes, then you go to step 2. Look at the shape. If the molecule is perfectly symmetrical, all those little bond tug-of-wars cancel each other out. The result? A nonpolar molecule. But if the shape is lopsided or asymmetrical, the forces don't cancel, and you get an overall pull in one direction, making the whole molecule polar.
Okay, so VSEPR is fantastic for predicting shapes. It really is. But it doesn't really explain why bonds form at these exact angles. It's a great model, but it's not a fundamental explanation. To get that, we need to dig a little deeper into the quantum mechanics of it all. And here is the exact puzzle that VSEPR just can't solve. We know an oxygen atom has its valence electrons in s and p orbitals, and we also know the p orbitals are all arranged at 90-degree angles to each other.
So if oxygen just used 2 of its p orbitals to bond with hydrogen, you would demand that the angle in water be exactly 90 degrees. But we can go measure it, and it's not. It's 104.5. So our simple picture just fell apart.
The solution is this really clever idea from Valence Bond Theory called hybrid orbitals. The theory suggests that right before bonding, an atom can kind of mix and match its basic atomic orbitals to create a brand new set of identical orbitals. And these new hybrid orbitals are perfectly shaped and pointed in just the right directions to match the geometries we already predicted with VSEPR.
And the connection here is just beautiful. If VSEPR tells you there are 2 electron domains, the atom undergoes sp hybridization to make 2 orbitals pointing 180 degrees apart. For 3 domains, it mixes 1 s and 2 p's to make 3 sp² hybrids in a perfect trigonal planar shape. And for our water molecule with its 4 electron domains, oxygen uses sp³ hybridization to create 4 tetrahedral orbitals. That perfectly explains that 104.5 degree angle we see in the real world.
This theory also lets us look closer at the bonds themselves. When orbitals overlap directly head-to-head, they form a really strong bond called a sigma bond. But what about double and triple bonds? Well, for that, you need a second kind of bond called a pi bond, which forms from the weaker, side-to-side overlap of the leftover, unhybridized p orbitals.
And the rule here is simple, and it never, ever changes. Every single bond is 1 sigma bond. A double bond is always 1 sigma and 1 pi bond. And a triple bond? You guessed it, 1 sigma and 2 pi bonds. The sigma bond is always that strong central connection holding the atoms together.
But, even this amazing model has its limits. It really struggles to explain things like why some molecules are magnetic. For that, we have to bring out the big guns, our final and most powerful model, molecular orbital theory. And this theory takes a totally new approach. It says electrons don't belong to just one atom or one bond, they belong to the entire molecule at once.
And here's the classic example that shows why we need this bigger theory. Let's ask a pretty simple question. Is a regular old oxygen molecule, O2, magnetic? Now, based on everything we've learned up to this point, the answer should be totally obvious.
And that obvious answer would be completely wrong. I mean, if you draw the Lewis structure for O2, you get a double bond, and every single electron is paired up. That predicts oxygen should be diamagnetic. It should actually be slightly repelled by a magnet. But if you do the experiment and pour liquid oxygen between the poles of a strong magnet, it sticks right there. It is clearly paramagnetic, which means it has to have unpaired electrons. Our theories just hit a wall.
And this is where MO theory becomes the hero of the story. When you build the molecular orbital diagram for oxygen, it predicts, clear as day, that the molecule has 2 unpaired electrons sitting in its highest energy orbitals. It perfectly solves the oxygen paradox where all our other simpler theories failed. It's an absolute triumph.
Now, a really powerful tool that comes out of MO theory is this idea of bond order. See, when atomic orbitals combine, they make 2 kinds of molecular orbitals: stable bonding ones that hold things together and unstable antibonding ones that push things apart. We can calculate the bond order with a simple formula: 1/2 times the number of bonding electrons minus the number of antibonding electrons. This number tells us how many net bonds there are, and it predicts whether a molecule can even exist.
So let's end with a quick thought experiment. We all know helium is a noble gas, right? It doesn't like to make bonds. But could you, in theory, smash 2 helium atoms together and make a diatomic He2 molecule? Let's use our new tool, bond order, to find out.
Well, if you had a helium-2 molecule, you'd have 2 electrons going into the stable bonding orbital, but you'd also have to put 2 electrons into the unstable anti-bonding orbital. So our calculation is 1/2 of 2 minus 2, which is 0. A bond order of 0 means there's no advantage to sticking together, no stable bond forms. MO theory confirms what we already knew from just looking around: He2 does not exist. So think about it. We started by just predicting simple shapes, and we've worked our way up to a theory that can predict existence itself, which really makes you wonder, what other molecular puzzles can these tools help us unlock?